Hello guys, welcome back to another episode of Consultant Explains Maths. Today I'm going to talk about another question that I found when I was in my junior year of university when I took complex analysis. I feel like this series is going to be me just discussing about questions that I got in my university years that I could not solve, and I want to go back to them and solve most of them. Let's try to do that. Anyways, this right here, as you can see, is the problem that we're going to solve today. So here, the first line is just a whole bunch of details. Basically, oh, I forgot. Before I continue, I need to give a bit of a preface. You'll need a bit of knowledge of complex analysis in order to comprehend this video. Otherwise, it will not make sense. Basically, first of all, you need to know what a pole is, when a function is holomorphic. I think that's it. You get the idea. I'm just gonna assume that you're familiar with these terms before continuing. Okay, without further ado, let's get started. So the problem statement is basically we just need to find the value of this infinite series or double infinite series because it goes from negative infinity to infinity. So you might be wondering, how does this question find its way in complex analysis? Well, it's because one of the ways one can solve this particular summation is by complex analysis. It's a very common, it's quite a common practice problem for students taking complex analysis, basically solving infinite summations like this. This thing would probably be frustrating and just a pain in the ass if you were to calculate it without knowing complex analysis. But using some tools from that subject, we'll be able to see that it is at least feasible to calculate. So what exactly do we have to do here? We have to turn to a tool or a theorem called the residue theorem. So I'm not going to go into too much detail about that residue theorem. Let's say we have a function fz that is holomorphic. I'm not entirely sure exactly where it's supposed to be holomorphic. Okay, apologies for that. And it has and we have this little contour C, for instance, and fz has poles, has certain poles inside of the contour. If you don't know what a pole is, basically poles are the zeros of 1 over fz. So if I were to take an easy example, for instance, fz is equal to 1 over z plus 1. Then if you substitute z equals -1, you'll see that it will introduce a division by 0, and therefore you can't really calculate fz when z is equal to -1. Therefore, it is a pole. To be precise, it's actually a z equals -1 is a simple pole because it only appears once in this expression. If I were to have another function, say gz 1 over z plus 1 squared, then z equals -1 is also a pole of gz, but this time it is not simple, rather it is an order 2 pole, a pole of order 2. Now we've got that out of the way. So if there are a whole bunch of poles of fz enclosed within the contour C, so here are the poles, then the residue theorem states that this equation holds. 1 over 2 pi I, the integral of fz dz taken in the contour C is equal to the sum of the residue of fz at P with P being the poles. Let's just assume that. Where the P is taken to be inside of C. No, okay. This is actually an abuse of notation. Basically, I'm supposed to say P inside, or basically in the interior of C, of the contour. But because it's too long, I'm just gonna say P in C here, just a bit of an abuse of notation. So basically, the residue theorem is commonly used to simplify the calculation of this side by looking at the values of fz, or sorry, not the values, but the residues of fz at certain points inside a contour, specifically the poles. This is a very powerful tool, and not just for things that are directly related to complex analysis, but also for things such as infinite summations like this. But we can't directly use the residue theorem to the function that we have at hand. We have to introduce another function. So gz equals pi cos pi z. Why so? Well, we're going to take a look at it in a minute. We're going to take a look at it in a minute. So gz has a very neat property where the poles of gz are the integers, as in every integer. Sorry, gz has poles at every integer. So it has poles at 0, plus minus 1, plus minus 2, and so on and so forth. How do we prove it? Well, we can rewrite this as pi cosine of pi z over sine pi z. To find the poles of gz, we need to find values of sine pi z. Sorry, we have to define values of z such that sine of pi z is equal to 0. And it so happens that if you plug in these values into the expression of gz, you'll make a division by 0, which means that we have the poles of gz. And this is true because of the periodic nature of the sine function. That's just the first one. Second, the residues. The residues of gz at each of the poles that we just found out is equal to 1 at each pole. So P equal to 1 for pole. P poles basically just to hand wave it a little bit. How would we prove it? Well, if we take a look at the definition of the residue for simple poles, we're going to have to calculate limit of z minus p times gz as z approaches p. So here we're going to have limit of z approaching p, z minus p times pi cos pi z. Oh yeah, okay, we got that. Right, so if you were to substitute z equals p directly into the limit, you're going to get a 0 times infinity indeterminate form. Because of this, we have to manipulate this into something that'll be more favorable. One way of doing this is by rewriting cotangent of pi z as cosine of a sine. So we have limit of z approaching p, z minus p. We're gonna factor out pi cosine pi z over sine z. Now, notice that this results in a 0 over 0 indeterminate form. And we can use L'Hopital theorem to evaluate this limit. So it's pi times limit. We take the derivative of both the numerator and denominator. We will obtain cosine phi z minus z minus p sine, so just the pi here, sine pi z over pi cos z. Now, if you were to substitute z equals p into this new limit, the right sum or the right quantity here will be 0. It cancels itself out. And here the cosine pi z in the numerator and denominator can also cancel out. And the pi's also cancel out. And because of this, we get the neat property that the residues of gz at each of the poles, no matter where they are, no matter if it's 0, 1, minus 1, is equal to 1. Using these two neat properties, we will be able to utilize this function in our calculation of the doubly infinite summation. So let's take a look at the problem at hand. Let's go back. Oops. Okay. Right. Recall that this is the form of thing. We're going to assume that fz now is equal to the terms of the series, but with z instead of n. So it's 1 over 9z squared plus 6z plus 1. Sorry about this little trespassing. So it is going to be pi cot pi z times fz z equals the sum of the residues of pi cot pi z fz at its poles that are contained within the quanta. So if we take a look back at the problem statement, we are given a whole bunch of other information here. So the Rn and the Rn and plus 1/2, CRn, all of these are actually used in the question, in the test. It basically means the radius when n is defined. And then CRn is supposed to be the circle. It's supposed to be the path that you're taking for the integration. And then DRn is the, what is it? The region, which is what is it? Is the interior of the path. So our path will look like this with anti-clockwise direction. And the radius is 1 over 2, like n plus 1 over 2. And then this path will be CRn. And then just for completeness sake, the inside of this circle is the area DRN, not the area. What is it again? The region DRN. So we can write this down as CRN, and then this is going to be P inside of DRN. Which I think is done to make it tidier when you're trying to solve the problem. Okay, so if we plug in the fz into the equation here, we're going to get this pi cot pi z over 6z, no, 9z squared plus 6z plus 1, z equals residue of have to wait until I finish this little long form. Okay. So here we have to notice that this function has poles at each integer because we have the cotangent pi z in the numerator. But don't forget the denominator, which would contribute to another pole. Notice that these are all simple poles, but there's one more pole that is contributed by the denominator. If we notice, this is equal to 3z plus 1 squared, and therefore it contributes to another pole, which is z equals negative 1/3, and this has an order of 2. The formula for finding residues for a poles of order 2 is going to be a bit different, but it's not much of a big deal. So we will expand this right-hand side. So we have n equals. Now notice that if we're taking a look at just the disk, the disk with radius Rn, we're going to limit ourselves to the poles that are inside of this circle, basically. Now I'm just going to say this is gz of p plus the other residue of gz when z is equal to negative 1/3. Okay. Now we have two things to do actually. We need to find the residue of gz at each integer. Not p, sorry. It's supposed to be n. And then residue of gz at negative 1/3. Notice that what we're looking at is the residue of pi called pi z of this thing. Sorry for the really messy handwriting right here. Pi z when it is equal to an integer. So we take the limit of z as it approaches n of pi z minus n cotangent of pi z over 9z plus 6z plus 1. Now, if we're to substitute z equals n to the denominator, it will not result in 0 for 0, so we can just factor it out. But you don't factor it. You get the idea. It's just a limit. It's just that the limit of the numerator does exist, so we can safely write it out like this. But then it's the numerator that will give us a bit of a trouble. But we just calculated this earlier, and it's equal to 1. So the left summation is going to be equal to this form. And this happens, and this is the case for all n, for all integers, basically, for all small n, as in the letter small n, just in case there's any confusion there. So 1 over 9 squared plus 6n plus 1. And notice that we have a very familiar form here, which is exactly the form we're looking for in the question. But instead of going from negative infinity to infinity, we're going from just negative n to n. And we're going to take the limit as capital N goes to infinity later on. And then we're going to have to find this one. Notice that this is an order 2, This is a pole of order 2. So there's a formula for that. So we will have n minus 1 factorial times the limit as z approaches p. It's going to be the, what is it? The general form. Limit of this expression. Okay, I'm not gonna rewrite this. Now we substitute n equals 2. Okay, this might be a bit confusing. This is k. K is going to be the order, just in case it's confusing enough here. So because the order of the residue is 2, and the pole is at negative 1/3, we're going to have 2 minus 1 factorial plus limit z approaching negative 1/3 z. Oh wait, hold on. This is a k. There's a k over there. Z plus 1/3 times pi over 9 of pi z. In this case, I'm going to divide the denominator by 9, as in by moving the 1 over 9 to the numerator. So just in case you're lost here, this is what we're doing. So here we can cancel out the z plus 1/3 squared, and it leaves us with this thing. So here, plus 1 limit z to negative 1/3 of this. Oh, sorry, I forgot. We have to differentiate it, sorry. So we have to differentiate it. Derivative of cot pi z with respect to z is negative cosec squared. So it's here p squared over 9 cosec squared pi z. And this, you can simply substitute z equals negative 1/3 into the expression here. So we have, and this time we're going to write it out in full. Minus pi squared over 9 times the cosec squared of pi over negative 1/3 is going to be 1 over sine of minus pi over 3 squared, which is going to be one. What is this going? It's going to be is going to be 4 over 3, because sine of pi over 3, because the sine of pi over 3 is, oh wait a second, because sine of pi over 3 is square root of 3 over 2, so squaring is 3 over 4, and then when you flip it, it's going to be 4 over 3. So you have it for pi squared over 27. Okay, and then don't forget about the left-hand side. Okay, that's CRN. Now, from this point, we need to take the limit of both sides as n goes to infinity, so that we'll be able to find the infinite summation that we want. It turns out that most of the time, this form here tends to 0. Obviously, we're going to have to show it, but as much as I would like to keep this video self-contained, it's actually quite difficult. Okay, so we want to prove that. Let's just write down the what is it? The function in full, called pi z of called 9z squared plus 6z plus 1 dz 1 over 2 pi. It doesn't really matter if I write it down. It doesn't really matter if I write down a 1 over 2 pi I. Here we move the 9 above, so we will get doesn't really matter actually. 1 over 9 pi cot pi z of z squared plus 2/3 z plus 1 in dz. Now we have to prove that this integrand is bounded. That is, we have to show that there exists an m, constant m, such that this is bounded. This thing holds. Now we can show this by doing two things. We can show it by actually we have to do both things. We show that pi cot pi z is bounded. Sorry, not bounded. Is bounded from above, and then this denominator is bounded from below. The latter is much easier. If you notice, this is z. Oh, by the way, I forgot. It has to be bounded at the disk, in the disk. So the disk that we set up earlier. So here we can rewrite this, rewrite the denominator as this. So that means if you were to find the norm or the modulus of z plus 3 squared, when z is, remember, on the circle of radius r plus rn or n plus 1/2, finding the modulus of z plus 1/3 is equivalent to basically finding the modulus of the circle that is shifted 1/3 units in the direction of the positive real axis. So this will be n plus 1, 5 over 6. It's going to be negative n minus 1/6. And notice that the modulus of z plus 1/3 in this case is going to be greater than n plus 1/6. So we have this inequality n plus 1/6 squared, which is great. So now we know that the form that we are using here is less than cot pi z over n plus 1/6 squared. It remains to prove that the numerator is indeed bounded, and unfortunately, it's kind of difficult, at least for me. However, we're in luck because this is actually not a new thing. Some people have solved it. It's actually on Stack Exchange. I'll give you a link about the boundedness of pi cot pi z at the disk. But you can also you obviously can prove it for yourself. But if you can't wait for that, I just want to progress this proof. I'm going to link you a Stack Exchange article on it. So we know that this bounded. We know that it is also. We know that this bounded is also dependent on n. So at least there's m something m prime over n plus 1/6 squared. And notice that because we have n in the denominator, if we let n go to infinity, this is going to tend to 0. Therefore, the left-hand side integral goes to 0. So now, bit of space here. So now, if we were to write it down in full, integral of CRN GZ dz is equal to summation of this lim, sorry. Okay, hold on, sorry. So this, okay, it's a bit messy, I know. If you are to take the limit of both sides as n goes infinity, we're going to arrive at the conclusion 0 equals this. I know it's a test. I'm not sure if this fact is supposed to be proven in class or not. But let's just assume it is. It might not be. So if so we can simply switch this into the left-hand side, and then we get the answer that this is equal to 4 pi squared over 27. Ooh. There's a very long way, and remember, we just skipped a step here. I do not actually know if you're expected to do this all in one sitting during the exam. But yeah, it's nice to know that you can actually do it. It's not impossible. It might just not be feasible to be done in, I think it's 20 minutes I was given. Maybe they expect you to have proven this in a class. Again, I can't remember it. If you are to take away the proof steps, if you just assume that the left-hand side integral does tend to 0, yes, it's going to be a very quick, what is it? It's going to be very easy question. But how would you know if it does converge? So yeah, still, I feel like it's quite a beautiful result here. And that's another question that I could not solve the first time around, solved. So yeah, right. See you again, guys. Hope you enjoyed this video. Bye.